Okay, welcome back, everybody. It looks like we have a lot of people online, and a few people probably will watch it later. This is the second lecture in machine learning or in 10701, and today we are going to actually see a real algorithm. As I said in the introduction, most of the initial part of this class is going to be about supervised learning. But in order, or many supervised learning algorithms will rely on methods from unsupervised or from density estimation. So the first thing we are going to talk about is methods to represent joint distributions and to learn parameters for joint probability distributions, because these will be useful in many downstream applications. So the first lecture, or the second lecture, this lecture is going to be on probability and MLE and maximum likelihood estimation. And I'm going to start with very, very brief introduction to probability. In fact, the main reason I'm doing this is really to set up the terminology. I'm not going to refresh too much about different issues related to probability. The assumption is that you already took the probability and statistics class as a prerequisite. And as we said in the recitation, so there's going to be a recitation on Friday, and part of the recitations will be some background on linear algebra, calculus, but also on probability and statistics. So those who are less comfortable or feel like too much time has passed since they took it should definitely try and attend that recitation. But I'm going to set up some terminology, and then we'll move to a discussion of how we are using different basic concepts of probability in order to estimate parameters and learn some properties of distributions. So we start with some notation. So random variable is a variable that refers to an event that we don't really know the outcome. Okay, so whether it will rain tomorrow or not is a random variable. We might have some probability, we might know something about tomorrow, or we might say, like, generally speaking, in August or in September it rains, I don't know, 60% of the time, so we have some probability about it.
Prof, do you want to share your slides?
Oh, it's not?
Yeah, or do you want us to look at the slides ourselves?
No, it's not. You can't see the slides. I'm showing them.
Oh no, it's on Piazza. But do you want to share it on your screen or something?
Oh, I can see it.
Yeah, I can see the slides too.
Okay.
Yeah, it's full screen for me, so
it's fixed for me. Thanks.
Awesome.
Okay, thank you. Yeah, so yeah, and as was mentioned, it wasn't, but all the slides are posted on Piazza. I usually try to do it the day before, definitely in the morning our time, but hopefully 24 hours before the lecture I should be able to post it. But I'm sharing my screen right now. Okay, so we have random variables. Random variables are, or the values of random variables come from domains. Domains are the set of values that a random variable can take. For example, we can have a binary random variable, whether, for example, the stock market will go up or whether it will rain tomorrow. That's a binary, yes or no. We can have a discrete random variable, so it can have one of a limited number of values. If we roll a dice, then it has 6 values. If we look at games in a football season, usually there are 16 games in the regular season, so you can have a discrete probability for the number of wins. Or you can have continuous probabilities, either within a specific range or unbounded in terms of the distribution. Okay, so each of these basically, or each of these domains basically represent a set of values that the random variable can take. There are a few axioms of probability that everything else is derived from them. So probability is always non-negative, and it's between 0 and 1. We usually refer to the probability of true to be 1, and the probability of false to be 0, and the union rule that for two random variables, the probability of A or B is the probability of A and B the probability of A plus the probability of B minus the probability of A and B. And this is these are the axioms, and a lot of the other things, or a lot of the other rules we derive, we obtain from probability, or we obtain for probability functions are derived or can be derived from these three axioms. There are other axioms, but these are the most commonly used. One thing we will use a lot in this class is something called priors, okay? So we can ask what's the probability that it will rain tomorrow? As we said, this is a random variable. It has a domain, a binary domain, yes or no. And we can assign a probability which holds in all cases, right? So any day of the year, I can say the probability that it will rain tomorrow is 20%, and the probability that it will rain tomorrow that it will not rain tomorrow is 80%. For example, just by the fact that maybe 20% of the days it rains and 80% of the days it doesn't rain. This doesn't use any additional information, for example, about whether it rained today or whether it rained yesterday and so forth. So this is called a prior. This is some belief I have in an outcome without any additional knowledge. I don't know anything about which day it is or what year it or which month or whatever. This is the belief I have in this random variable. There's also something called conditional probability, and conditional probability is the belief in an outcome given something that you know about something else, right? So for example, what's the probability that it rain tomorrow given the fact that it rained today? Or what's the probability that it will rain tomorrow given the probability, given that the forecast says it's going to rain? So what's the probability the forecast is wrong, for example? Okay, so this is called conditional probability, a very, very important concept in this class. And conditional probability of two variables, A and B, is basically the probability of A equals 1, for example, conditioned on the fact that B equals 1 or B equals 0. It doesn't matter. The conditional is on some value of B. Again, so A could be rain tomorrow, B could be rain today, and I can ask what's the probability that it rain tomorrow if I know that it rains today. Maybe there is a rainy season somewhere, so if you know that it rains one day, it's very likely that it will rain the next day and vice versa. So this gives you a lot of information. Some places it can give you very little information. So maybe the probability of rain in a location is always 50-50, so it doesn't really help you the fact that it rained today. But sometimes it can help a lot. Okay, and of course, the probability of a conditional event can be very different than the probability of the prior. Okay, for example, here, if we look at A with respect to this box, we can say the probability of A is 20%, but if we know that we are in B, then the probability that we are in A, let's say B is the green box, then the probability that we are in A is 50%, because 50% of B is A. Okay, so this is just... Now, conditional probability can be computed or can be derived from observations, right? We usually do it, and you can use that to show some differences. For example, if I want to compute the probability that I slept in a movie, I can just count how many times I slept in the movie. Okay, so let's say I went to the movie, in this case, 8 times, and I slept 50% of the time. So I can say the probability that I slept, if I don't know anything about the movie, then the probability that I'll sleep in the movie is 50%. But if I know that I like the movie, the probability changes, right? So if you want to know what's the probability that I slept, given that I like the movie, you restrict yourself to the rows of the table that only contain liked. And you can see that in this case, I only slept once of the 4 times. And if I didn't like, I slept 3 times. So if you know that, or if you know some other fact about the random variable, or for example, or if you know some other random fact, not necessarily about the random variable. For example, if you know that I like the movie, then it can change your opinion or decision about whether I will sleep in it. Okay. And this brings us to something called, so this was conditional distribution, conditional probability. Okay, so we had priors, we had conditional probability. The next thing is something called joint distribution or joint probabilities. And joint is basically the probability that 2 events happen together. We usually represent it with an and, or honestly, most of the time with a comma. So comma means that A and B happen together. Okay, so for example, in this case, we can say, what's the probability that I both liked the movie and slept in the movie? Okay, so this is the probability of 2 random variables, like the movie and slept in the movie. Both of these have a probabilistic outcome. And we can ask, what's the probability that both of them occur or happen together? Now, one thing that is very important to know, and of course a lot of you know it, is that if two variables are independent, then the joint is basically the product of what's we call the marginal, the individual probabilities. So if A and B are independent, so for example, if I'm sleeping in the movie regardless of whether I like it or not, then the probability of A and B is the probability of A times the probability of B. However, in most cases, most of the variables are not independent, right? So in this case, for example, we already seen that there is a much higher probability that I will sleep in a movie that I didn't like and stay awake in a movie that I like. So in most, and that's generally true. So generally speaking, we cannot assume that two random variables are independent. But if we do assume that they are independent, then this joint probability factors very nicely into the marginal probabilities. Now, whether or not they are really independent is one thing. Whether we make the assumption that they are independent is another thing. And one of the things you will see in this class is that sometimes we make assumptions that we know are wrong, but makes our life easy in terms of learning. And sometimes, even though the assumptions are wrong, the outcome is not so bad. Okay, so that's something to keep in mind. Later in the class, we will actually rely a lot, or we will use a lot, this idea of independence, both in the first part of the class on supervised learning, something called a naive Bayes estimation, but also in the other parts where we talk about graphical models, Bayesian networks, hidden Markov models, Markov random fields, and so forth, where we rely on this quite a lot. Okay, so again, joint distribution, you can compute it, for example, from tables, right? So for example, let's say we have some table about some ranking for different classes, right? So this is the size of the class, this is the time, regular semester over the summer, and this is the evaluation. Okay, so we can ask what's the probability that the class size is greater than 20 and the summer. So in this case, we need to go over the table and find cases where we have both this one greater than 20 and the time is summer. And in this case, it's only 1 out of 10, so we can say it's 0.1. And oh, by the way, you can see that, of course, they are not independent, because if you just look at this and this, so the marginals themselves, if you multiply them, you don't get 0.1. So you can see that they are not independent because the joint is different from the product of the marginals. And similarly for other things. Okay, so in most cases, random variables are, in many cases, random variables are not independent, and you cannot assume that they are independent. Okay. The last thing before we start talking about a bit more involved machine learning issues is something called the chain rule. And the chain rule basically links, and that's a very important rule because, as you will see, it's directly leading to something called the Bayes rule, which we'll use a lot in this class. And in fact, a lot of the algorithms we will talk about in this class are based on it. So the chain rule basically links conditional and joint probabilities. And it works for all of the probabilities. So not just those that, not all probabilities. It works for all of the random variables, not just those that are independent or dependent. It works in all cases. So basically what the chain rule says is that you can write a joint probability as a product of a conditional probability and the marginal probability. And that's true for any two random variable. In fact, this can be extended to more than two random variables as well. So that's very important. Again, why is this true? I mean, I can illustrate it with some cartoon, but basically what the chain rule is saying is that the joint probability of A and B is the probability of A condition on B times the probability of B. This is, of course, symmetric. So you can also do the same to say the probability of B given A times the probability of A, it will be the same, right? A and B are, there's no meaning to the ordering of A and B. So both of these will work. Why is this true? So the idea is that the joint probability of A and B, right, so if we look at this, this is the large set of values that this is the domain basically of A and B, let's say, and this is the joint of A and B inside this domain. What the idea is that you can factor it as the probability of B inside the domain, okay, and the probability of A given that you are inside B. Okay, so this is larger, of course, than the joint. So this contains it, but then when you multiply it by the part that A contains inside B, you get back the joint part itself, okay? So this is, so again, the joint is here, right? This is the joint of A and B, and you can break it down into two pieces. One is B, because the joint has to be inside B, and second is the part that A occupies inside B. Okay, so this is the chain rule. Again, we are not proving it, but we will rely on it. And if you believe the chain rule, or if you agree with the chain rule, then the next step is something called Bayes rule. And again, I moved very quickly and I didn't even prove anything, but this is just, again, setting the terminology. So Bayes rule basically is just the chain rule, but we use the symmetric part of the chain rule in order to get the probability of one conditional probability as a function of another conditional probability. So we know that the probability of A and B is the probability of A conditional B times the probability of B. As I said, this is symmetric, so it's also the probability of B conditional A times the probability of A. And then if we just take this part here, then we can say that the probability, the condition of A and B, A, or the probability of A given B, is the probability of B given A times the probability of A divided by the probability of B. Why is this useful? It's useful because sometimes it's much easier to compute one side of the condition compared to the other side. So if it's easy for us to compute or to find out the values, so it's even easy for us to find the values of one side of this conditional probability, let's say B given A, what Bayes rule tells us is that it's very easy or possible for us to infer the other condition. So if we know B given A, we can get A given B. Okay, and we need the priors as well. But if we if we know the priors on one side, we can easily get the other side. And that's extremely useful. Again, in many cases, as I said, in algorithms, I'll show you an example in a second why this is useful as well. But this is a very useful fact that comes directly from the chain rule. Okay, so this is called Bayes rule. As I said, and you can see in the names, naive Bayes, Bayesian networks, a lot of algorithms in machine learning, not a lot, but there are several algorithms in machine learning that basically use this rule quite heavily. One before last, I guess. A comment about a Bayes rule. So sometimes it's actually harder to, or sometimes it's also, so we said already that we want Bayes rule because sometimes it's much easier to compute B given A compared to A given B. Sometimes we can't directly also compute the marginal over a specific variable. And this is where we can use the summation rule, okay? So the idea here is that, and let me see if we can do this. Yeah, so Daniel, we still didn't solve the problem, right? With the Google Jamboard, right?
Yeah.
So I'll use this, okay. Right, so P of A and B, right? If we write it like this, oh, sorry. So what we can say is P of B equals P. I'll get used to it. Okay, so this is always true for any, let's say in this case, discrete random variable. If we have continuous, we just need to take the integral. But basically, if I sum over all the values that another random variable can take, let's say I have two random variables. It doesn't matter if they are dependent or independent. If I have two random variables, and I want to know what's the probability that, let's say, B equals 1, if I sum over all the values that A can take and compute the probability of A and B, then I basically sum over all the domain and I get back the probability of B. Okay, so this is the summation rule. And if that's the case, we know then this equals, right, sum over A, P of B given A. Right, this is just the chain rule. Right, P of A and B is P of B given A times P of A. So this is a way to move from the marginal probability over B to a conditional probability and the marginal over A, which may be easier to compute. So this is what I did here. Okay. So this is what I did here, right? So I'm summing over A, P of B given A times P of A, which is exactly, I mean, I'm just replacing P of B with P of A and B, and then P of A and B, I use the chain rule to get that. And this is the final version, I would say, of Bayes' rule. Okay, this is the version that we will use in most cases. This basically only requires knowledge of the probability of B given A and the probability of A for all values of B and A. But we don't need to know directly the probability of B or the probability of A. Okay, so this is just a representation of the sum rule that I've shown you, but that's okay. Last thing, everything that we said already can be applied also to continuous distribution. So this is not just a function of discrete distribution where we sum here, we sum over A and B. It's also true for continuous distribution, and we'll discuss continuous distribution in a second. Oh, yeah, soon. Okay, good. So any questions about, so I move very quickly, but any questions? I know the chat has a lot of things, but I don't know if there's any relevant questions. One of the TAs or Daniel can. Anybody has any questions? Yeah, okay, so.
There's one in the chat.
Yeah, so can I explain what it means to sum over all probabilities of A? Yes, so let's say I want to compute the probability that it will rain tomorrow, okay? And we want, and basically, let me do this, okay? So I can do this quickly, hopefully. So let's say I want to compute the probability that it will rain. Let's say the probability that rain tomorrow is 1, okay? So what I can say is the probability that rain tomorrow is 1 is equal to sum over rain today. Okay. Well, let's this is P of R T equals 1 N. Okay, so this, what does it mean? The probability that it will rain tomorrow is the probability that it will rain tomorrow and it rained today, plus the probability that it rained tomorrow and it didn't rain today, right? There's only two options for, in this case, this is A. This is A and this is B. Okay, so A is the event that it rained today, right? It either rained today or did not rain today. There couldn't be anything else. Now, the probability that it rained tomorrow is the probability that it rained tomorrow and it rained today. These two are two separate things. They cannot happen together, right? And the second thing is the probability that it rained tomorrow and it didn't rain today. So this, and these are the only events that can happen, right? There's no, we are not missing anything, and we cannot add anything for this to be, right? I mean, there's only two options for A. So if we sum over all the probabilities for A, or all, not the probability, all the options for A, and compute the joint, then each of these is a separate set of events, and the sum of these is all the probability that it will rain tomorrow. So that's the idea of what I was talking about. And that's true for any discrete variable. And for continuous variables, basically, it's the integral over this thing. Okay, yeah, we need to move. again, hopefully most of you have some, or at least I think we'll have some questions in the problem, or at least one question in the problem set that will let you play with it. Let's do an example of why Bayes rule is useful, and then move on to discuss some estimation issues. So some of you have heard about a recent development in the COVID-19 testing, a great new product that came out from Abbott Labs. They promise a $5 COVID test that you can do very quickly. I think it still requires some medical assistance in order to take the samples, but other than that, this looks great. There is one downside which wasn't emphasized, but maybe we as a class should take into account. This test has a 1.5 false positive rate. False positives means that if it says that you are positive, there is there is 98.5% probability that you are indeed positive, but 1.5% that you are not positive. Okay, so this is false positive. It also has a pretty high false, well, the false negative rate is about 97%. So for 3% of the population that has the infection, it will say that it doesn't. But let's focus a bit more on the false positive. Okay, so the false positive is 1.5, which doesn't seem like a lot, right? 98.5% of the time, it's correct in terms of positive. So now this seems like a great test to administer very widely because it's very cheap and we can just run it through all the population. But a good question will be, out of all the positive results that this test generates, how many of them are really positive, right? So let's say there's 100 positive results. How many of these 100 are really positive? Can anybody tell me? Let's say 1,000. If it gives you 1,000 positive results and it has 98.5 false positive, sorry, 1.5 false positive. Anybody can tell me?
seems like a lot of people in chat are saying 985.
Yeah, okay. Good, that's true if, right? So this means that right. This means that if you are if the right, so if the test says that you're positive, right? If the test says that you're positive, then right, sure. I guess phrase the question correctly. Let's say that again, so the test has 1.5% false positive rate, meaning that of the false positive, right? So if you are negative, it will tell you that you are positive 1.5% of the time, okay? So false positive means that, let's say there's 1,000 people that are negative, then basically 15% of them, 15 people will be positive. That's correct. Now, of the ones that of the ones that the test set is the test. Okay, so let me rephrase the question. Of the ones that the test said are positive, how many are really positive? And that the answer here is not going to be 15 out of 1,000 because it really depends on the people who take the test, right? So for example, if all the people who took the test, let's say all 1,000 people who took the test are negative, 15 of them will be declared to be positive, right? But 0 will be really positive. So the percentage of those who are actually positive is 0, basically, right? If all the people who took the test are positive, and the test has, then everybody the test will say it's 100%. So the answer is not going to be, not going to be, no, I'm going to show you some numerical calculation. I just want to make sure that the fact that the false positive rate is 1.5% does not mean that the actual error on the test that on the population is going to be a 1.5%. It really depends on the underlying distribution in the population. Okay, so let's do an example. Maybe it will be clear. Okay, but let me show you an example and explain why this might not be that as good as it sounds. So maybe I confused you a bit, but hopefully this will be clearer now. Okay, so this was not actually the first test that. So let's do an example and see what I meant. So let's say we have a test not for COVID, but you can think about it of COVID. It's the same thing, where we have a false positive rate of 1%. Okay, so of the people who are healthy, right? If you are really negative, 1% will stay. The test will say that it's positive, and in general, 99.9% of the population is healthy. Let's say in Europe, that's more or less the case right now for COVID, and 0.1% are infected. Okay, the test is perfect. It doesn't have any false negative. So if you yeah, so it doesn't give you any false negatives. So if you are positive, it will say that you are infected. If you are negative, right? If you are negative, it will give you 1% false positive. Okay, that's the test. So 0 false negatives and 1% false positives. And we know that only 0.1% of the population. So the question is, what is the probability, if the test says that you are positive, what's the probability that you are really positive? Or what's the probability that you really are infected, given that the test said that you're positive? And again, this is AIDS, but you can think of it as COVID. How do we do this? We can use Bayes' rule. So Bayes' rule says, what's the probability of AIDS given the test, right? We want to know what's the probability that you really have the disease, let's say AIDS, if the test is 1. If we want to use Bayes' rule for that, it's the probability that the test is 1 given, right? Given that you have AIDS, times the probability or the prior on this, divided by the probability that the test is 1. Okay, so these two things we can actually compute already from the information, right? What's the probability that t equals 1? What's the probability that you are that the test is 1 if you have the disease?
1.
Right. So it says, right, we know that if A is 1, then there's no false negative. So you will be. What's the probability that what's the probability that you have the disease? It's very low, right? It's the probability of AIDS is 0.01, basically. Okay. And what's the probability that the test is 1? For this, we're going to use the other part of Bayes' rule, which is basically, we will basically factor this, as we said, we will sum, so we will treat this as P of B and then do sum of B given A times P of A, right? So this is the probability of the test, the test is 1 given A equals 1, and the probability that the test is 1 given that A equals 0, okay? So this is just, this is B and this is A, okay? So we just do what we did before. And now we actually can just plug in the values from above. So as people said, the probability that the test is 1 if A is 1 is 1, the probability that A is 1 is 0, 0, 1. That's the same here. And here we are doing the opposite. So the probability that A is 0 is 0.999. And the probability that the test is 1 if A is 0, basically the probability that the test will say a false positive, you don't have it, but the test says if you do have it, is 0.01. And when we put it all together, we see that only 9% of those that the test says are positive are really positive. Okay, or only 9%. Oh, sorry. So the probability that you really have the disease or the infection, given that the test is positive, is only 9%. So if you take 1,000 people and you tell them, and this is, by the way, this is assuming a 1%. If we have 1.5%, it will be even higher, right? So for the Abbott test. So basically, it means that if we test 1,000 people and the underlying infection rate is 0.1%, okay. So of the 1,000 people, roughly 900 that, sorry, not if we test. If we test 1 million people and 1,000 come up as positive, 900 of them are actually not really positive. And that's really because of the underlying prevalence in the population.
Okay.
Yes, question? So basically, this tells you that, 1.5 or whatever % is really good, but you have to be very careful about how you apply the test, because it's only good if the population is 50-50. 50-50, then it's pretty good. But if the population or the underlying infection is very skewed, then even a small false positive rate can lead to very, very large mistakes in real life. Okay. So this is an example of using Bayes' rule, and again, this was on an AIDS, but it applies equally well to. By the way, one way to mitigate this is to test on a more likely population. That's why, for example, in many of the many places, including the US, the recommendation is only to test you if you have been exposed to individual or if you have some symptoms. In that case, the probability of infection is much higher. So the underlying probability is much higher. So even if you have 1% false positive rate, most of the people who are positive are really positive. So that explains why, and there's been a lot of criticism why widespread testing is not offered to everybody. But again, if there is even a relatively small false positive rate and a very low prevalence of the infection, this will lead to a lot of misdiagnostics. So you can criticize some issues related to testing, but there are some. It's not completely unscientific. This anyway, but that's a separate discussion. Okay, so let's talk about continuous. Unless anybody has a question, anybody wants to ask a question about this, so that's fine. Okay, good. Okay, good. And Daniel and or the other TAs, if you see any question, just alert me, okay, please. Good. Let's continue. So we mainly talked about this discrete distributions, right? Probability of rain, not rain, probability of a test being positive, negative. There's also, or in this class, we are also going to deal quite a lot with continuous distributions. There are several types of distribution. I just wanted to say that. And again, we are not, I didn't cover almost any distribution, except I mentioned binary, but there's also something called multinomial, uniform distribution, and so forth. Maybe, or maybe this will be covered, or at least some of them will be covered in the recitation. I do want to emphasize that there are continuous distribution and continuous and continuous distributions are very useful to model real-world values. For example, if we want to model the height of students in this class, we usually are not going to use discrete distribution because height is a continuous value. Even though we measure it maybe to some, I don't know, feet and inches, you can go into much higher resolution in terms of the points after the decimal. So in this case, we have continuous distribution. There's a lot of different continuous distributions. One of them very popular and very successful, or one that we'll use quite a lot, is something called the Gaussian distribution, which basically assumes that a variable is distributed with some mean, which we call mu, and some variance, which we call sigma squared. Okay, and like with the tables that we use to estimate the values of discrete probabilities, we can use observations to estimate the values of continuous distribution. For example, we want to determine how much time do students in this class sleep. Okay, so we can just take observations, right? So this is an observation of the number of hours that students sleep in this class, and then based on these observations, we can compute, like we did before, some parameters of this distribution. And in the next part, we will talk about exactly how to use it. The important thing about this type of distributions is to fit. So we have an assumption about the model. So we have an assumption about the distribution, that it looks like this, basically, that it has a mean and some variance. And we have a set of observations, and our goal in this type of distribution is to fit the model to the observations. So in this case, right, in this case, the distribution, the red distribution has a mean of 0, but in class, in this case, we see that the distribution is slightly different. So the goal is to really fit the distribution to the observation in the best way we can. And again, we will talk exactly how to do it next. But this is true for discrete distributions, and this is true for continuous distributions. And more generally, in continuous distribution, right? For example, this is a covariance matrix, so we can also use relationships between, so it doesn't have to be a distribution over just one variable, like we did, for example, in the discrete case. We can have a multivariate distribution for continuous values as well. And in this case, for example, if I want to compute what's the joint probability of sleep and GPA, for example, which is also a continuous value, I can compute some parameters and then learn a distribution that tells me something about the probability. So if you give me the values of X, right, you can compute what's the probability that you will see someone with a very high GPA that sleeps very little. And similarly, what's the probability of someone with high GPA that sleeps a lot, and so forth. And in this case, we use this is a continuous distribution. This is called Gaussian multivariate distribution. It's characterized by a mean vector in this case, and a covariance matrix. Okay, so this is very brief introduction to probabilities and to terminology that we will use throughout the course. Next, we are going to talk about or we are going to start dealing with aspects related to machine learning, and this is how do we estimate parameters for these probabilities. Okay, so that's the first set of algorithms we will learn. Any questions before we move to that? Anybody has any questions? No? Okay, so the next, I would say, so the next part is going to be two different ways to estimate parameters of distribution. So we said, what's the probability of rain tomorrow? I said it's 0.2, but how do I get to this 0.2? What's the probability of rain conditional tomorrow, given that today it rained? I said it's 0.4, but how do I get to that? So we said, we already showed the way based on the tables by just counting, but counting, makes sense, but it's not, there's no underlying theory of why this is the right thing. And how do we deal with continuous distributions? How do we estimate parameters? So the first thing we really want to do is something called density estimation. And density estimation deals with the ability to estimate the values of parameters for distribution. So for example, if I assume, so the assumption of what type of distribution it is a separate issue. So for example, a coin flip, I can assume that it's a binary distribution. A height, I can assume that height in this class is a Gaussian distribution, but this is just an assumption. Maybe it's not a Gaussian distribution. Maybe, I don't know, maybe it's some exponential distribution, something else. So we are separating the assumption about what type of distribution this is and the parameters. So for this class, we assume that we know the type of the distribution. The goal is to find the parameters of that distribution. So for example, if I have a coin flip, I assume that this is a binary distribution, binomial distribution. And I want to know what's the probability for heads and what's the probability for tails. That's my goal. Or if I have a die, I want to know what's the probability for 1 to 6. Or if I want to estimate the probability of height in this class, I assume that this is a Gaussian distribution. And my goal is to estimate the parameters. Okay, this is the goal of this class for now. How do we get the assumption about the probability? We are not going to discuss. In fact, for the most part, we will just assume based on some background, on our domain knowledge. Okay, but assuming that we know something about what type of distribution this is, what is the next step? How do we go about finding the parameters of the distribution? What's the first thing we need to do to find parameters for a distribution? Let's say a coin flip. What would you do to find the parameters of this distribution? Anybody?
Collect samples.
Absolutely right. So the first thing, and that's what we showed in machine learning, right? The first axis of machine learning is data. Without data, we can't do anything. Of course, you can make an assumption, but the first thing you want to do in order to predict the probability of a coin flip, binomial distribution, or some Gaussian distribution, for example, height, is collect information from students about their heights or flip the coin several times. Okay. Now, okay, so we did that. And the question is, how do we use it? Or the question we will try to answer in the next class, or in the next, half an hour or whatever we have, is how do we use this a set of observations in order to estimate the probability? And there's two major directions. One is called a MAP estimate, or maximum a posteriori. And this is using some Bayesian approach. I'm going to talk about it first, primarily because we are not going to use it a lot in the class. You will still work on it in the problem set, but this is not something that we'll use a lot in this class. It's important to know that it exists, and it can be useful in some cases, but it relies on domain knowledge that we prefer not to assume if possible. The second approach is something called maximum likelihood estimation, which I'm going to introduce later today, and we will use extensively in this class. In fact, almost a lot of the different algorithms rely on. Okay, so let's start with the MAP estimate, what's known as the Bayesian approach. As I said, we will not use it a lot, but it's something that is good to be familiar with, and we will refer to it in some cases. Okay, so what is the Bayesian approach to estimating parameters? So let's say you're going to determine the probability of a set of coin flips, okay? So you collect a few samples, right? That's the thing that was suggested, and obviously that's the first thing we do. Unfortunately, there's a limit to how many samples we can collect. Maybe 5 is too little, but in practice, there is a limit to how many samples. Now, of course, if you have a binomial distribution, it's only 2 values, that's easy. But if you want to collect information on biology, right? So you have tens of thousands of genes, there's a limit to how many cells you can measure. Or if you want to collect pictures, right? There's a limit to how many pictures you can collect, but each one has maybe thousands or tens of thousands of pixels. So learning probability distributions for these high dimensional spaces is very hard. So there's a limit to how many samples you will collect for a complicated data problem. So if you collect a set of samples, let's say 5 coins, you can say, okay, let me just count how many times I see heads, how many times I see tails, and say that the probability for heads is 60%, the probability of tails is 20%, is 40%. That's good, but it's dangerous, right? Because you know that you only collected relatively few samples, so it could be very biased, even though, even though the probability is 50-50, you will see something slightly different. So what can you do? One thing you can do is use the Bayesian approach. What does it mean to use the Bayesian approach? Bayesian approach means to use the conditional assumptions, or condition on some assumptions that we have, and in this case about the domain or assumptions about the world. For example, we can assume that most coins, not all of them, maybe some people are cheating, but most coins are pretty balanced, right? So we can assume that most coins are going to be 50-50. In that case, if we assume that most coins are 50-50 and we flip the coin 5 times and we see that 3 times it came head and 2 times it came tails, we are going to say, even though we saw 60% of the outcomes as heads, we are not going to say that the probability of heads is 60%. We might say it's 52%, because yes, we saw a bit more heads, but we assumed that the heads-tail distribution is close to 50-50. So the idea is to combine your prior belief about the world, which is 50-50, with the observations. Okay, so this is called a MAP, or maximum posteriori estimate. How do you do that? Well, there's lots of ways to do it. The thing we like the most is something called conjugate priors, and I'll discuss them in a second. But the basic idea of this assumption, of this estimation process, is to have some prior assumption, get some observations, and try to combine them together in order to get a revised model of your distribution. So initially, you don't see anything, you assume 50-50, you start to see things, you start to update your distribution. Now, the more samples you have, or the nice thing about this approach usually, is that the more samples you have, the more your estimation is based on the samples and less on the assumption. If you have very few samples, the assumptions play a big role. If you have a lot of samples, the assumptions are going to be the weight of the assumptions is going to go down. So that's a good way to combine assumptions and observations. Okay, so how do we do that? We do it using Bayes rule. That's why this is called Bayes estimation. Basically here, unlike before where we try to estimate the probability of an observation, here we treat the parameter as a random variable. Okay, that requires some different thinking. Basically, in this case, theta is the parameter. In this case, it's the probability of the coin flip. And the goal is not to find out what's the probability of the next coin being 1. Oh, well, that's the ultimate goal. But the goal is to find out what's the probability that the parameter, let's say theta is 0.6, 0.5, right? Our goal is to find out the probability, the distribution over the possible values of the parameters. So in this case, the parameter can go between 0 and 1. That's the probability of head. And we want to compute the probability of the parameters given the data. Now, how do we do it? Based on we can use Bayes' rule, right? It's the probability of the data given the model times the probability of the model. In this case, this is the prior divided by the probability of the data. Since the probability of the data is the same under any, right? So the probability of the data is basically the data is given to us. We don't, right? We are not going to do, right? So this is basically sum over all possible probabilities and basically the probability of the data given the model times the probability of the model. Then we can remove, we don't really need it. And basically the probability of the prior scales with the probability of the data given the model times the probability of the model. So we can ignore the denominator in this case because it doesn't depend basically on the thing we want to optimize, which is the parameter. Okay, so this is the idea of Bayes learning, basically, that we have some prior and we want to learn a posterior. Posterior is our new belief after we saw the data, and that probability is going to scale with the likelihood, how good this prediction is, times how much we believed in it in the first place. Okay, so let's see an example. Okay, so yeah, so usually we take some, we use it, yeah, we can, that doesn't really matter. The important thing here on this slide is the fact that we want to use conjugate priors. Conjugate priors are priors where the posterior, this is what we call the posterior, this is the estimation we have after we see the data, seems very similar, or the function that we use for the posterior is very similar to the function that we use for the prior. Again, this will become clear in a second, but the basic idea is that if we have a posterior that is similar to the prior, it's pretty easy to estimate and it's very easy to update. We don't need to walk too hard to update once we see the observations. So let's do an example for coin flip. Okay, so for coin flip, we are going to use right, the Bernoulli model where the probability so we assume that the coin flips are independent. So the ordering doesn't matter in this case. And the probability of a set of observations given a model is just the probability of heads and the probability of tails, right? So we have theta, which is the probability of heads to the power of the number of times we saw heads, and 1 minus theta, which is the probability of tails, to the number of times we saw tails, right? Because that's the probability of, basically, if we don't care about the ordering, that's the probability of the events happening, or this, that's the probability of each of these, right? The probability of each of the coin flips, and we just take a product of all of these probabilities. So this is the probability of the data given the model. If we have an assumption, or if we have the probability of heads, this is the probability that this is the probability we will assign to this set of observations. Now, if we assume a prior as a beta distribution, so a beta distribution is a specific type of distribution that is basically defined. This is a definition as theta to, so we have two values that define this. These are inputs to the function. These are user-defined values, and we'll talk in a second about how to define these values. But once you have these two values, the probability of a specific theta in using the beta distribution is theta to beta h type minus 1 minus theta beta t minus 1 divided by b. This is this function. Again, this is a normalization function. Basically, make sure that this sums to 1 for any value between 0 and 1. So it's always positive, and it sums to 1 because this is a probability. So this is just a normalization factor. This is the definition of a beta probability. And this is the prior we put on theta. Now, once we have this prior, remember the posterior is this times the likelihood, right? This times this. When we do this times this, what we get back is another beta distribution. So we basically, right, remember the posterior is this times this. This is the likelihood, this is the prior. When we multiply this by this, you can show that we actually get back a new beta distribution. The difference between the previous beta distribution and the current beta distribution is that the new beta distribution includes the observations. So beta H plus alpha H, and this is beta T plus alpha T. So basically we get back a beta distribution, but now the beta distribution that we have for the parameters includes the observation that we have. Okay, so let's see an example and see why this is useful. So one thing to realize is that the prior basically tells us two things. First of all, it tells us how much we expect the heads and the tails to be the same to begin with. So as we said, if we think 50-50, then the beta H and beta T should be the same, obviously. But that's not enough because they can be 1-1, they can be 2-2, or they can be 50-50. The difference, so even if they are the same, the magnitude implies something about our confidence in the belief. If we think that most coins are 50-50, but maybe a lot of them are not, then we will use relatively small values, let's say 2, 2, 3, 3. On the other hand, if we are pretty sure that almost all coins are 50-50, we should use very high values for both. So we can say 100 and 100. The difference is that the higher the values of the priors, the more samples you need to override them, right? Because when we combine the two, you can see that we have a weight from the samples and we have a weight from the priors. The higher the values for the priors, the more samples you need in order to move away from the priors. Okay, so this is some examples of a beta distribution. Maybe this is some priors. And then after we observe, right? After we observe a coin flip, you can see that the distribution changes a lot. So this is, you can see the ratio is the same, 3 and 2, but here, because the values of the betas are very small, then the distribution is much larger, whereas if the values of the betas are very large, then the distribution is very skewed. Okay, so yeah, so this is the idea of conjugate priors, and right, so this is an example for our, let's say we see another, we flip the coin and we see another, in this case, right, we see another head. So you can see initially we have beta H and beta T are 2 and 2, but after we flip a coin and we add it to the distribution, we saw one head, the distribution changes to become more concentrated on the likelihood that it's head. Okay, so the parameter, in this case, the probability of, right, the probability on this, I think, yeah, let's say, right. So so in this case, the probability of this is probably the probability of tails is going to be right. So we are going to have a higher probability for heads rather than for tails. So 0.1 minus 0.3 is probably the probability of heads. Right. So conjugate priors are true for or can be used for binomial distribution. They can only be used for other types of distribution. And again, the challenge is to find the correct conjugate priors. For multivariate discrete distributions, we can use something called the multinomial distribution. So multinomial distribution, very similar to binomial or Bernoulli, basically assumes that the probability of the data given the model is, again, the probability of each of the possible observations to the power of times, to the number of times we saw it. So this is the number of times, so 1, 2, and so forth. So this is the likelihood of the data given the model, and we also have the prior on the model. This is called the Dirichlet distribution, and again, very similar. It's just a product of the original or the priors on each of the different values divided by some normalization function that makes sure that this sums to 1, and every value is between 0 and 1. Okay, so this is the prior, this is the likelihood, and the posterior is just a summation like we did before of the priors and the observations. So again, if you flip a die with 6 values and you don't know anything, you can say, look, I assign a value of 1 to each one, and then when you see more and more observations, you can update your distribution or your probability based on the Dirichlet distribution. Okay, so we are almost done. The main challenge is that what we got out of this, I mean, this whole discussion, right? We actually get a distribution. So we get a distribution over parameters. These, let's say, these are parameters for heads. So this is the PDF of 0.2, 0.4, 0.5, and here, I don't know, 0.3 and so forth. So we get a lot of different values, but at the end, we want to have just one value for this distribution, right? So we want to have a probability for heads. We don't want a distribution over the probability of heads. Because if we want to make some, or if we want to use it in some downstream algorithm, or if we want to use it for some prediction, we really want to know what is the probability of heads. And this method does not give us the probability, it just gives us a distribution. So how do we go from there to a probability? The answer is what's known as the MAP estimate, or the maximum a posteriori estimation. The maximum a posteriori is the value that leads to the highest value for the combined, basically, for the likelihood times the prior. Okay, so we have a distribution over these values, right? This is the distribution. This is the distribution over, right? This is the distribution over the a product of the prior and the likelihood. And there is one point here, which is the maximum, or at least right, there is argmax for this function. There could be multiple points, but there's an argmax value for this. Well, in the beta distribution, there's only one, but there could be others where you have multiple points. Anyway, there is the maximum to this function, and this is what we are interested in. We are going to take the argmax of the distribution, which again could be multiple points. In the beta distribution, it's going to be one. And we are going to select, or in most beta distributions, right? We saw already that in 1, there's no, but in most cases, the beta distribution gives one value, and we will use that as the estimation of our probability, right? So again, long story short, if you want to use the Bayesian approach, what you have to do is start with a prior, make an assumption about the distribution of the prior using some conjugate function, have a lot of observation, update the conjugate function based on these observations, and choose the mode, basically. Right, so this is the mode of the distribution. And again, in the beta case, this is going to be just the count, alpha plus beta h over this. But this can be different for different functions. So you choose the mode or the highest point in the distribution, and this will be your prediction for the MAP estimate. Now, you don't need to use the MAP estimate. If you want to use the entire distribution somehow, some way you can do that. You can integrate maybe over the distribution. So this really gives you a distribution, unlike other methods we'll talk about. But in most cases, we are actually interested in the MAP estimate, and we are going to find the one individual value that will give us the result or the probability of the distribution that we are looking at. Okay, so this is called maximum a posteriori or Bayesian estimation. As I said, we will, I think, ask you to work on this in the problem set. Although most of the algorithms we'll discuss in class will not use this method, the main drawback of this method, I mean, it's a very nice method. The main drawback is the fact that you need to come up with you need to define a prior distribution. And that's hard in two ways. One is you don't know which type of function is the best to define that. And second, even if you know, let's say, a beta distribution, you don't know what should be the values of the prior, or in most cases, it's hard to tell. Okay, so that's why, again, I'm not saying it's not a good direction. It's definitely a good approach, but in most cases, we are not necessarily using it. Okay, so this is MAP estimate. Any questions about this? About MAP estimations? Good, okay, so now, finally, we are on our way to discussing a real algorithm in the machine learning class, which is good. And the first algorithm we're going to discuss is also about density estimation, but in this case, density estimation using something called the maximum likelihood estimation principle. So this is another way to perform density estimation that does not require or does not rely on any assumption about the priors. It does rely on you need to define a probability distribution. So as I said in this class, and in fact, in most of the classes, we will assume, or we will use, or we will define a probability distribution for the data, and the goal will be to learn the parameters. We are not going to learn which type of probability distribution we're going to use. Okay, so for example, for coins, we will assume a binomial distribution. For dice, we will assume a multinomial distribution. For height, we will assume a Gaussian distribution and so forth. And the goal is to estimate the parameters from observations. Okay, so we have an input, a set of values, right? So in this case, we just rely on the set of observations. We have a density estimation, a method, an algorithm, basically, and we get out probabilities. That's the goal of this algorithm. And this applies very widely, right? So it applies to binary, to coin flips, predicting whether an alarm will sound, to discrete variables, right? Dice or car model, to continuous variables, height, weight, temperature, and multivariate predictions can also use this method. So density estimation is widely used, predicting population, predicting a lot of other things. And as a component, this is going to be something we will use in a lot of other methods. So in naive Bayes and in all the Bayesian networks and hidden Markov models and a lot of other methods. We will rely on logistic regression, a lot of supervised and other methods, and even learning under uncertainty will rely on this. So this is a very important method that is used quite a lot in machine learning. Right, so in many cases, we use density estimation as an ingredient in algorithms, and sometimes we use it in combinations with other types, something called EM, expectation maximization, which we'll get to, and as I said, in other algorithms as well. Okay, so how do we do this? How do we use the density estimation method? It turns out that the solution, or the way to use density estimation, or the algorithm, is very simple. Basically, it just requires us to count, but it actually has a very nice underlying motivation. So it's not just that we count like in the table, we just counted and we said that's the probability. We can actually show that the estimation that we get is based on some very strong, or not strong, but very reasonable assumption about the data. Okay, so here is the solution, basically. And in a second, we will try to motivate why this is the solution. So if I want to know the density, if I want to predict the probability of an event, right, I just count how many times I saw that event and divide by the total number of samples that I have, right? So if I want to count what's the probability of heads, I count how many times I saw heads, I divide it by the total number of coin flips I did, and this is the probability of heads. If I want to know the probability of 1 in a dice between 1 and 6, I count how many times I saw 1, I divide by the total number of times I flip the dice, and this is the outcome that I get, or this is the prediction that I make. And again, this is for discrete distributions. For continuous distribution, we'll talk about in a second, or not in a second, but in a few slides. But generally speaking, this is the idea of density estimation. You just count and basically take the fraction that you see, right? That's what we did in the table. The question, of course, is why is this the right thing to do? Or what is this counting based on? So in order to answer that, we are going to define something we called a likelihood. I already referred to it, although I never formally defined it. So now I'm going to formally define a likelihood of a data given the model. A likelihood of a data given the model is if we have some probabilistic model for the data, it's the probability of all the observations conditioned on the model. Now, if we assume that the observations are independent, we can make it as a product of the different observations. If the observations are independent, we can do it as a product. If the observations are dependent, we need to do it as a joint. But in this case, let's assume that we are doing a coin flip. Each coin flip itself is independent. So we want to know what's the probability of X, which is X, each X is a coin flip, conditioned on the model. The model in this case is the probability of heads. Okay, and we can write it as as the probability of a set of observations, x1 to xn, conditioned on the model, conditioned on the probability of heads. And because we said each coin flip is independent, we just get a product of the probability of each of the coin flips conditioned on the parameters. This is termed the likelihood of the data given the model. The model is, and again, in this case, the model is very simple. It's just the probability of heads, but the model can be much more complicated. For example, we can ask, X can be an image, and M could be a probability of a specific cat image of cats, for example. So M could be very complicated model or very simple model. As long as we have a probabilistic or a way to represent this in some probability term, we can write this likelihood function here. Okay, so this is just the likelihood, the probability of the data given the model. This is called the likelihood. Okay, so given that this is the likelihood, right? So M is the, right? So M could be the probability of heads or the probability of a die and so forth. So now, given that this is the likelihood, the next step is something called the maximum likelihood principle. The maximum likelihood principle states that if we have a set of observations, we would like to find a model that maximizes this function here. This is the likelihood of the data given the model. Of course, we don't know the model, but there is a value for the model, in this case, a value for the probability of heads that will maximize this function. And that's what we want to find. We want to find the value of M that leads to the maximum for this function here. This is called the maximum likelihood principle. Okay, so once we define the likelihood is a function of the model, and our goal is to find the value for the model that leads to the maximum. So in our case, for example, the theta or the M is the probability of a coin flip, right? So this is just the product of the probability of the first observation times the probability of the second and so forth, okay? And we assume that the coin flips are independent. Right, and we already said that given, I mean, the answer is to do the counts, but the question is, why is this the way to do the counts? So in order to find the best solution for this problem, we really need to find the value that maximizes this probability. And the way to do it is by maximizing a combinatorial function. How do we maximize a function? Well, we learned this in linear algebra or in calculus. You basically take the derivative with respect to the parameter, equate to 0, and then hope that this is the maximum. Sometimes this is the minimum, so you have to take the second derivative in order to show that this is really the maximum. Okay, so this is what we want to do here. If we have a likelihood function, the likelihood is a function of a specific parameter. The parameter in our case is the probability of heads or the probability of tails. It's one, it doesn't matter. And so if we have that, we can write it as a function of this parameter and then take the derivative with respect to that parameter, equate to 0, and hopefully we'll get the maximum. Okay, how does this apply to our data? So we have the probability of the data given the model. D is the set of flips, M is the model. In this case, Q basically is the probability of heads, and we have N1 observations of heads, 1 minus Q, N2, right? And our goal is to find an argmax over Q of Q to the power of N1 minus Q to the power of 2. This is the likelihood of the model. This is the likelihood of the data given the model, and this is the maximization part. Okay, so our goal is to find Q that maximizes this function here. Again, how do we do it? We take the derivative. Right, so again, this, I mean, right, so if you're using the full binomial distribution, you also have this, right, N1 plus N2, choose N1, but this doesn't depend on Q, so we don't really need to use it for the argmax. Okay, so this is the data likelihood, Qn1 minus Qn2. And if we take the derivative with respect to Q, then we need to do some steps, right? This is N1, Qn1, and so forth. This is something you can look at, and I mean, you can go through the simple math after the lecture. But the bottom line is that at the end, we end up with N1 equals N1Q plus N2Q. Basically, Q equals N1 over N1 plus N2. What does it mean? It means that the probability of heads is the number of times we saw heads divided by the total number of observations. Exactly what we said before, but now coming from the maximum likelihood estimation principle. So if we are interested in finding the maximum likelihood, if we are interested in finding the parameter that maximizes the likelihood of the data given the model, this parameter will be N1 over N1 plus N2. This is true for the binomial distribution, It's also true for other discrete distributions. So, for example, you can show. Do I have it? 1 second. Yeah, sorry. So this is true for binomial, but it's also true for other discrete distributions, including multivariate distributions, where you just count and you see the or basically, if you take the derivative with or the partial derivative with respect to each of these parameters, you will get the same solution. Basically, for example, the probability of 1 in a die is the number of ones divided by the total number of samples. So the number of 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, any questions about maximum likelihood estimation? Again, very important concept. You will play with it in the problem set, I think. So you will do some derivation of more complicated or maybe even continuous distributions. I will discuss continuous distributions in the next lecture as well, but this can be done for other distributions as well. Any questions about this? So this is very important concept in there.
Yeah, we actually did get a question that I'm not 100% sure on. Is the assumption always that the observations are independent in MLE, or is that just in this case?
No, so as I said, MLE is basically writing the, so MLE tries to maximize the likelihood of the data given the model. If the samples are independent, then the likelihood is just the product of the samples given the model, each one. If the samples are not independent, then you cannot assume that then the probability is some joint probability. Sometimes some of the samples are dependent, some are independent. Of course, if everything is dependent, it might be very hard to compute the maximum likelihood estimation, but it doesn't mean that the likelihood. So maximum likelihood can be divided into two parts. One is the likelihood, and the other is the maximum. The likelihood function should be correct based on what your assumptions are. The way to maximize it is a separate issue. Obviously, if the things are independent, it's much easier for us to maximize. But there's no requirement that things are independent. Maybe there is a way for you to maximize even if things are independent. Or are dependent. That's your problem, basically. In most cases, we will assume that samples are independent of each other. For example, if we take a lot of pictures, we will assume that each of the, in fact, most cases, we will assume that the input is drawn from something called an IID, so an independent distribution of the input space. Yeah, but again, this really is separate. I mean, it's just based on the assumption. Okay, so yeah, I wanted to say maybe one more thing, but maybe I'll get, I mean, this is really important for the next step. So maybe I won't mention it now. I do want to say, yeah, so maybe we'll finish here. I want to say this is the last time that I'm teaching for 1 hour and 20 minutes without a break. Going forward, don't worry, I will take, so we won't have a formal break, but I usually have a quiz during the lecture, basically that is not graded, so we're not going to grade the quiz, but it is asking questions about some of the stuff, and this provides some informal grade that also a break that also provides information about the class. So I apologize. I mean, I do have a quiz question, but I didn't teach the information that you need for it. So next time we will do a quiz, or maybe even more than one. So it will be hopefully a bit more relaxed. But on the other hand, you should have Piazza ready. So the quizzes are going to be administered on Piazza. So please be ready with Piazza for the next lecture. Okay. I guess last announcement: there's no class on Monday, so it's Labor Day here in the US. Yes, most of you are in the US right now. So there won't be a class on Monday. And on next Wednesday, we're going to finish maximum likelihood estimation and move to classification. And we will also release the first problem set next Wednesday. I think one final thing, there is no office hours this week, but we are going to have a recitation on Friday. So you should definitely, you're more than welcome to attend the recitation. And that's it. I think we're done. See you.